Thank you for invitation to Bure-sur-Yvette. This is already the nth time I'm here, and I'm all the time very happy to be able to talk to you. And this time, this time I will talk about a very simple problem, which is mathematically related to the exponentiation of power series in the following sense. Here under point 1 we have a power series which starts with n equals 1, and you have a sort of exponential generating functions with the coefficient Cn in the exponent, and we call them Cn, and then the result of this exponentiation is another series which starts this time with n equals 0, and the coefficients are called an. And this is a very old problem, and I will present some quasi-known result, so my exposition will be sort of expository, but nevertheless the problem is old one, and it appeared in many fields, and Cn are usually given, and one is interested in obtaining A of n. And why I called it C, because this problem appears in many fields of mathematics and physics, and I will be mostly concerned with the combinatorial aspect of that, but it appears also in the theory of numbers and in field theory and in many other fields. And now, usually, as I said, Cn's are given. How to obtain An? In general, they will be formulated in terms of hypergeometric function, or rather generalized hypergeometric function, and I will present some results. The usual general formula for that is not very transparent. It has been obtained in general form by several people, but I was interested in particular cases, and I wanted to have a maximum simplicity of the forms. So this is maybe a naive approach, but let's see what happens. Oh. So once again, Cn, what are the properties of this expression which I quoted before? First of all, you can show, but I will not present proofs here at all. Just I will enumerate some properties of the formula. So first of all, if Cn are integers, you can show that An are integers. The second is that when Cn are given, then An are uniquely determined by Cn. Why I called An and Cn? Because in the graph theory, this formula is very well known. It's called exponential formula, and it is, in fact, it has been conjectured and proven for some physical problems by Uhlenbeck and Ford many years ago. In combinatorics, it's called Riedel's formula, and it is well developed in many combinatorial handbooks, including Stanley's book. This relation between An and Cn is called exponential transform, okay, for evident reasons. Now, I just mentioned that in the graph theory, Cn represents usually number of connected graphs. If you have some system of producing graphs, then Cn is number of connected graphs at the stage n, and An is a number of all graphs. So schematically saying, exponentiating connected graphs, you get all graphs. That's why I call them A and C. Okay? Now, from the practical point of view, two situations are interesting. When situation A, when Cn are non-zero for almost all or maybe all of n. And the second situation, when Cn are non-zero for some n. And both of these situations are interesting in their own right, because what we need is some tractable closed form formulas, and I will show you that in this context, the formulas are all expressible through generalized hypergeometric functions. And this is rather advantageous from our point of view, because these functions are extremely well implemented in algebra, in computer algebra systems, so you can really calculate the things very quickly. So now the first case which interests us is the most important one for other application. This is the case when all Cn are equal to 1. When all Cn are equal to 1, this formula number 2 tells us what is the definition of the numbers Bn. So this is a double exponential in formula 2. So it's exponential of exponential from which we have subtracted the term 1. And everybody knows what it is. These numbers are called Bell numbers, and they are illustrated here for initial values of n. And they count the numbers of all partitions of n distinguishable objects, for instance, when they are labeled by colors or by some indices, into some boxes, which are indistinguishable. So boxes are indistinguishable, but particles or objects are distinguishable. So, of course, trivial example is n equals 3. You have, for 3 objects, you have 5 partitions, which are enumerated here. So there is a partition into singletons, there is a partition into itself, and there are 3 partitions into pairs and 1. So total number of all partitions is 5. That's why the number B of 3 is equal to 5. Now, there are many beautiful and interesting formulas obeyed by these Bell numbers. They are listed in many books, and some of them carry some particular adjectives like beautiful or amazing or surprising. And in fact, I myself was attracted to the field of combinatorics by just seeing these formulas for Bell numbers in some old Russian books. So now, what interests us are constrained or restricted partitions. So what are restricted partitions? These are partitions where we don't have some kind of boxes. So we say we don't have collecting particles of certain numbers. So partitions of 3, but without doublons or doublons, there are only 2, because there are 3 partitions which contain pairing, which contains 2. So therefore, the number without doublon is equals to 2. And the numbers, partition number without singletons is equals to 1. And without tripletons equals to 4. Now, we have analytic and closed form formulas for Bell numbers in a very convenient way. So one would be happy to have also a closed formulas for restricted partitions. But I will explain you how it is done. So first of all, I told you already that all this set of problems can be formulated in terms of hypergeometric functions. And this starts with Bell numbers themselves. And this is not very well known. And I had the chance to write down these forms. I found them by playing with the definitions. And apparently it wasn't done before. So Bell number, this one which I defined in the previous slide, is a spatial value of hypergeometric function with the parameters n-1, n-1. And the first list contains the upper parameters, and they are all equals to 2. And the second list are lower parameters of hypergeometric function, and they are all equals to 1. And the value is equals, parameter value is equals to 1. So already you see that these Bell numbers are expressible through hypergeometric functions. Now, how do we treat the case of these restricted partitions? So restricted partitions will be partitions where in the series, in the exponent, you omit certain monomials, or you remove a series of monomials. And I will explain you with one example here, and I will follow with other examples. So imagine that you do not have singletons in your partition. So you don't have boxes which contain one object. So how does it translate into generating function? You simply subtract the power t to the power 1 from your generating series. When you subtract that, you expand the whole thing, and then you get numbers which are here with green. So if you remove singletons from your formula, so you just remove the power t. If you remove singletons and triplons, you remove t and t cube divided by 3 factorials. And these numbers, after having removed terms, I note with a specific number underlined. It means that there is no singleton, and here there are no singleton and no triplets. So the whole principle of that is that every monomial in the expansion of exponential represents partitions. And if you remove this monomial, then you will not have partitions of this type. Okay? So, well, this can be proven rigorously, but this is the everyday bread of combinatorists. So now the question is how to obtain a closed form expression for such numbers. And well, first of all, I will make a reference to a fantastic source, which is the Encyclopedia of Integer Sequences, which has been nurtured and invented and taken care of by Neil Sloan about 50 or 60 years ago, and it grown up into a huge data collection of about 400,000 integer sequences, and it has enormous value because it contains documentation of these sequences, references Maple and Mathematica programs, asymptotics, and literature. So in analyzing all kind of Bell numbers and other numbers, the use of this encyclopedia is absolutely basic. So before I go to this restricted Bell numbers, I will mention another fact which is also of certain importance in this field. It is the fact that this decomposition into different kinds of partitions of a set is characterized by the Stirling numbers of second kind, known already for over 200 years. And it turns out that this classical Stirling numbers of second kind again can be expressed through specific spatial values of hypergeometric functions. So not only Bell numbers themselves, but Stirling numbers of second kind, classical ones, can be expressed through hypergeometric functions. And this relation is nothing else but the relation which characterizes hypergeometric function. Okay, so the question is what we do with restricted partitions. Okay, so the okay, sorry, it jumps without my, okay. So the simplest case of restricted partition, which has been addressed to by many people, inclusive Jean-Bernard Zuber, I believe, it is the one where we subtract all singletons, and we simply do not have singletons. So look at this series, which is here. This sequence has a 0 at n equals 1. So if you have an object of one point or one color, one object, so you don't have partition of 1. So the number of this partition is equal to 0. And now this is the formula which is given by the multiplication of series, and this is the formula of restricted partition without singletons. Okay, now paradoxically, to obtain the appropriate Stirling numbers for this problem is not a trivial matter, and in fact it is known, but I will not quote this formula. The demonstration of this formula is complicated, and in fact I will talk about this related problems a little bit later. Okay, now I will explain you now the following situation, that we want to treat restricted partitions which either do not have singletons and m-tons. It means boxes which are composed of single objects and of m objects. Either they do not have that, or the other type of partitions, which I considered previous slides, which have only singletons and m partitions. So either they do not have at all these two cases, or they have only these two cases. In this situation, we simply use spatial tools which were developed by Giuseppe Dattoli in Frascati, Roma, which consists of certain generalization of Hermite polynomials. And this generalization is extremely simple, namely, it is given by this formula. And you remember, so now we have polynomials of two variables. Hermite polynomials have only one variable. Now we extend this definition to the second variable y, okay? And in fact, this extension is given by this formula. So you see, in case of classical Hermite polynomials, the relation is here. So classical Hermite polynomials correspond to the first variable, which is equal to x, and the second variable is equal to -1. And now, so this is this extension. And in fact, these polynomials treated by Dattoli were not completely new, because they entered the field much earlier, and they in fact are known as Gould-Hopper polynomials, and also under other name Kampé de Fériet polynomials. So they were introduced by some previous researchers in this field. But what I want to stress is this formula, that these polynomials, which were defined here, they again can be expressed through hypergeometric function, but this time it has m upper parameters and no lower parameters. But because of the structure of components of the parameters here, you see that this function, hypergeometric function fm0, with this argument, is a polynomial. So suppose that we want to treat the case where we let's take this expression. So this is in preparation to treat the case of restricted partition without singletons and without m-tons. So if you just look at this expression, this involves the power series whose coefficients are just these hypergeometric functions, where x and y are parameters of these generalized Hermite polynomials. So using this result, if you want to have a closed form formula for partitions without singletons and m-tons, its exponential generating function will have this form, and since you now have this first part of the expression, which contains Bell numbers, this will be given by the Cauchy product of series, which can be done in this case, which is not always possible, but in this case it is possible. And finally, appropriate numbers of generalized Bell numbers of restricted partitions will have this form. And now look at this form. Here we have Bell numbers, which again are hypergeometric form, and you have this hypergeometric form fm0. And now this can be easily treated by computer algebra systems, and here we have some examples, and I have marked here that some of these sequences are known. For instance, for m equals 2, it means without singletons and without doubletons. This is sequence in the Encyclopedia of Integer Sequences, number A006505. But for m larger than 2, these sequences are enumerated here, and they are not in the Sloan encyclopedia. You can call them new, but of course They are not new in the sense that they existed without our knowledge. Okay? So you see that this kind of simple problem of restricted Bell numbers has a analytic solution oh, sorry. So now that was partitions without some boxes, without singletons and mtons. Now I'm going to, oh, sorry, no, this is not right. Okay. So now I'm going to treat opposite situation where we force to have partitions having only singletons and mtons. So this is an opposite situation, but it's not really very much different, because by forcing to have only kinds of partitions, then you just change the sign here. For instance, exponential generating function with partitions of singletons and mtons, which will have here signs plus. And the expression now B1 with the upper line has this simple expression. Once again, it is, of course, hypergeometric. So this kind of partitions are again listed in Sloan Encyclopedia. But what I want to say is that there are complications, because the appropriate formulas for Stirling numbers, which will characterize this generalized Bell numbers, are not trivial, and in many cases one doesn't know how to obtain them. But there is a hope. I still have a hope that maybe we'll be able to do that. That's why I have left here some blanks. So next stage is to try slowly to have some more generalized cases. So before we had no singletons, no mtons. But now we have something, let's say, step by step. So we have no doublons and no quartons. Okay? Once again, we can do the same thing that we did in the previous example, and the closed form formula contains now this function, and now there are Bell numbers once again, but now the n minus 2k, so there is a multiplicity which appears, and again Bell numbers and hypergeometric numbers here. And these are the numbers, as far as I know. They are not by Sloan. Now, the next step, complication, is no doublons and no sextons. Okay? So you may say this is a very naive approach, but, well, that's what I am able to do. So this is the formula, once again, but now it contains, here was F20, here is F30, and so on. So these are the formulas. So next thing is the next step of complication. These are partitions without triplons and without non-nons. Okay, I invent a terminology which is based on music. So no boxes with 9 and no boxes with 3. So once again, this is the formula, and you see that there is a notable change of the argument of hypergeometric functions. And this is given by some formulas which I didn't specify here. Anyhow, these are exact formulas. And once again, we have formulas for these numbers, but for the moment, we don't have formulas for appropriate Stirling numbers for this case. And now I will talk about some drawbacks and difficulties of this problem. So it seemed at the first sight that, okay, by complicating the thing, we will finally arrive at a general formula. And in fact, this is not so simple. 10 minutes, yeah. Yeah. So look, if we have a particular case that we have removed from our set of partitions two monomials whose exponents are mutually prime. So we removed doublons and quintets. And lo and behold, I don't know how to obtain the formula, because there is an arithmetic problem which has been pointed to me by some friends. And in fact, it appears that you cannot solve this problem. And in fact, the sequence is known, but there is no formula for that. Well, but I'm not a specialist of arithmetics, but maybe some colleagues will have comment on that. So this corresponds to the fact of removing partitions, doublons and quintets, okay? But by keeping only doublons and quintets, we still have here sign plus, but the problem is the same. We don't have a formula. Maybe it exists. Now, I want to tell you that we don't have a formula, but we can have a numbers. By what kind of reasoning? Simply by expanding in Taylor series. By doing that with machine, you get a series which is well defined, but we don't know the formula for the members of the series. So this is for me an open problem. Okay? Now, practically the last thing before last thing I want to say is that there is a hope to treat this kind of problems with some restriction. So our friend Giuseppe Dattoli published 2 weeks ago a paper in Archives, which is listed here, where he proposed to define a kind of Hermite polynomials which will be of many variables. You remember here in this treatment before, we had this Hermite polynomials of 2 variables. Now he has a way of treating Hermite polynomials of many variables, and they can be recursively defined. Okay, but I will have no time to give you the formulas. But it appears that then you can obtain some kind of expression for this kind of problem. But remark one thing, that you always must have a linear term. Why? Because the linear term is needed for 2 variable Hermite polynomials. Without linear term, there is no definition of two variable Hermite polynomials. So you can treat this case with sign plus and with the sign minus, but only with keeping with a linear term. So this is a drawback of this formalism, but well, at least you can formulate you can write down certain expressions for these numbers, which was not possible before. But this expression has a recursive character, so some people may like it or not. But remember, the previous expressions were not recursive, but they were just given by a nice 5 centimeters formula. Whereas here it is not possible anymore, but the expressions give the right numbers. And where do we take our right numbers from? By doing Taylor expansion, which is also done by computer algebra systems. But our task is not to have operational formula, but to have analytic closed form formulas. Okay, so let's say there is a hope, but this is a very fresh development. I had only very little time to try to see whether it works, but it does. So now the only thing I want to add is the following thing. That this generalized Hermite polynomials, which I was talking about before, which okay. You see, oh, sorry, it jumps without my, okay. If we look at this thing, so this looks quite arbitrarily because you say, well, you introduce the parameter m, which is different than 2, okay, and you have two variables, yeah. But in fact, it turns out that these polynomials are solutions, no, h n of x, y are solutions of very nice differential equations. And here is m. The formula which is here. Here is m. You see? This is d m d x m x y with the initial value h n m equals x n. So you see what this kind of equation is a sort of generalized heat equation. When
H is missing.
Second member.
H is missing.
On the right hand side.
here?
No,
Above.
It's above, to the right.
To the right side.
No,
Second member. Right.
Ah, H. Yeah. Of course, H, yes. H, N, M, X, Y. Okay? So now if we look at this equation, I still have 2 minutes.
Yes.
So when M equals 2, then this is the classical heat equation. And when M is larger than 2, this will be a generalization of heat equation with higher derivatives. Okay, and this has been the subject of many studies, but it also can be reformulated with a different philosophy, namely, this is, oh, sorry, I didn't write, this is x, this is y equals 0. This is x and 0 equals x n. Okay, so this is sort of heat equation, as I said, with the initial value equal to monomial. So what does it mean? It means that the sort of evolution which is contained in this equation tells us that the monomial expands to polynomial through evolution under y. Of course, these are polynomial solutions of this kind of equation. Engineers are looking for solutions which can be normalized. So these are not general solutions, but anyhow, these kind of solutions are relevant for themselves. Okay? So I believe that this kind of problems can be of some interest for other people than combinators. That's all.
Thank you very much. Yes.
Is there a natural path to Q-deforming all these numbers by using, for instance, Q hypergeometric functions?
Probably yes, but I cannot tell you at the moment. But anytime hypergeometric function appears somewhere, then there is a question, how about Q hypergeometric? But some people are very enthusiastic, and some, like Marek Bożejko, yeah, he will immediately ask the same question, right? But other people say, okay, that doesn't have physical applications.
Yes?
Can you say a little more about the arithmetic problems that you encounter when you have coprime exponents?
Well, I tried to do the trivial multiplication of series, and then the formulas do not function. And I think you pointed out to me some
We discussed this point, but what we call closed formula did not appear, of course. All depends, it's a matter of text, what is a closed formula.
But you cannot write the expression for the numbers which you obtain through differentiation. But this is certainly related to the case when they are not mutually prime. But I said if you include the linear term and you apply the new formalism of Dattoli, then you get formulas, but not, let's say, they are closed form, but recurrence type. Okay? Not of the same nature as I pointed out.
Yes, dear Mark.
Yeah. So can you come to the first page, because there is a beginning of story, and that is nice equation, which I think I discussed sometime with you, and maybe now you know. So that equation, most important. Of course, this is
this one.
Oh, that one. That one. Oh, introduction. This is that equation.
The next one. The
Next one?
The first one. Yeah, first one.
Oh.
And that is, if I remember, where appears in many papers of Sergei Karol.
Yes.
Related with interlacing measure, and also with the Young diagram and a representation theory of permutation group, for example.
Mm-hmm.
And that parameter which you have has the interpretation in the language of Young tableau or Young diagram, and that was done by, I say in my talk, right, with Wierszyk and Karol. Did you, because you give only to us numbers. I am Pythagoras church, I like numbers, but I would like some interpretation. Yeah? So like Bell numbers is just moment of the Poisson
Yeah,
measure.
okay,
But this is partition language is just mathematics, but should be some physics, right? Because in Karol and Wierszyk, they give you to us some physical interpretation.
It's
So
very
you have
difficult.
also some here, some physics or some because this is language or like very interesting, but only one numbers or sequence of numbers. But it would be nice to have some measure, because this is Poisson measure, Gauss measure. So
measure
Mike said also here measure, but did you have some other language that nice measure appears with your formulas?
Yes, I can. There will be discrete measures for which I can give you some generating functions, but I don't have too much. This will be kind of processes which will be restricted Poisson process, but discrete. They will be always discrete.
Thank you very much.
Yeah.
Thank you very much. We should discuss later.
I am sorry, but this is time to thank again the